Okay, this question is abstracted from your textbook, page 412 Brown, the AP textbook, and it's an example of how to use the combined ideal gas law. The combined ideal gas law is P1 V1 N1 over N1 V1 is equal to P2 V2 over N2 T2. You'll notice that sometimes when you have problems with this gas law, if a quantity is the same before and after, you simply cancel the variable. Just drop whatever variable is not being used. In this particular problem, the pressure is kept constant, so P1 and P2 are crossed out. Also, the amount of gas, N1 and N2, is unchanged, so N1 and N2 are also crossed out. And the ideal combined gas law reduces to V1 over T1 is equal to V2 over T2. So let's read the question and see what information it's giving us. A large natural gas storage tank is arranged so that the pressure is maintained at 2.2 atmospheres. There's that constant pressure. Before and after, it'll be still 2.2. On a cold day in December, when the temperature is minus 15 degrees Celsius, the volume of gas in the tank is 28,500 feet cubed. Now, some of you may wonder, why is a non-SI unit being used? It happens. This equation will work no matter what units you use, as long as you're consistent before and after. So if you use feet cubed for volume in the initial state, use feet cubed in the final state. Even if it's a non-SI unit, the answer will work out accordingly. So the question continues, what is the volume of the same quantity of gas on a warm July day when the temperature is 31 degrees Celsius? So just one proviso, when you put in the temperature, you have to put in the absolute temperature. When you work with gas laws, you have to use the absolute temperature scale, because the absolute temperature scale is based on Kelvin, where 0 Kelvin is equal to absolute 0, which is equivalent to minus 273 degrees Celsius. That's the temperature at which all gases have no kinetic energy. So all gases would turn into solids at that temperature. So the problem suggests a set of initial and final conditions, which points to the use of the combined ideal gas law. Initial conditions, final conditions. When you have only one set of conditions, you use PV equals nRT. We've canceled the variables that appear on both sides of the equation, so the equation basically reduces to V1 over T1 is equal to V2 over T2. Because in this problem, 3 of the variables are given, and we are asked to solve for the fourth. Temperature must be entered in the absolute temperature scale, as I said before, in Kelvin. And the conversion factor is to add 273.16 degrees to the Celsius temperature. So if the temperature is 0 degrees Celsius, that equals 273 Kelvin. So we enter the conditions, 28,500 feet cubed, the temperature in Kelvin. The final set of conditions, the final volume is the one thing we don't know. And the final Kelvin temperature, 31 degrees Celsius, is the same as 304 Kelvin. And minus 15 Celsius is the same as 258 Kelvin. So it's the same, degree Celsius and degree Kelvin is the same unit of measure. The only difference is that the scale has been slid down 273 degrees. So we isolate the variable V2, and we solve for it, getting the volume is 33,000 feet cubed. We're only allowed 3 sig figs, so we report the answer to 3 significant figures, 33,600 feet cubed. On the next problem, similar nature, we have that a 0.5 mole sample of oxygen gas is confined at 0 degrees in a cylinder with a movable piston. The gas has an initial pressure of 1 atmosphere. The gas is then compressed by the piston so that its final volume is half the initial volume. The final pressure of the gas is 2.2 atmospheres. What is the final temperature of the gas in degrees Celsius? So we use the combined ideal gas law. And because we don't know the volume, either before or after, all we do know is that the initial volume is twice the final volume. So we let the final volume equal to x, and we let V1 equal to 2x. When we enter those values into the equation along with all the other parameters, we see that x cancels, and we end up with the number 2.
because the volume is twice as much. We then solve for the final temperature, recalling that it will be in Kelvin, and then subtract 273 from the Kelvin temperature to get a final temperature of 27.14. We're only allowed two significant figures in the final answer, so we have to report it as 27.